Okay, this is chapter 16. It deals with the adaptive immune system. The adaptive. What the adaptive is, the difference is, it's kind of the third line of defense, and it's able to recognize specific antigens, specific foreign bodies. So it will respond, say, if you have an infection of the influenza virus, and it can distinguish one strain of influenza virus from a different strain of influenza virus. And so if you get H1N1, you will build up antibodies against that, respond to it. But if you get H1N3, that's considered a totally different strain, and so you would not have initially any protection against it. So the adaptive immune system is going to be very specific in its response to very specific types of pathogens. There are certain things that you will see along with it, such as specificity, the way it's induced. It will make clones of memory cells, and it is able to recognize these invading cells as not part of you. This is going to involve the lymphocytes. If you remember, this is one of the subgroups. There were 5 subgroups of leukocytes. So the lymphocytes are those. Now there's 2 different types of lymphocytes. There are the B lymphocytes, which we just call the B cells, and the T lymphocytes, which we call the T cells. The B cells will mature in the bone marrow, and the T cells will mature in the thymus. And they are involved with the adaptive immune response, of which there's 2 subgroups. There's the cell-mediated, and there's the antibody immune response. The T cells typically are involved initially more with the cell-mediated, and the B cells are. This is just a slide showing the lymphocyte on a blood smear. Remember, the lymphocytes are the ones that the nucleus comprises most of the mass of the cell. The cell-mediated immunity, just kind of as a very quick summary, because this is what the chapter is going to be looking about in detail, is those T lymphocytes. There'll be a process in which they will activate additional specific types of T cells. So there's several different kinds. Things such as the 3 types would be the helper T cells, the cytotoxic T cells, and the regulatory T cells. They are going to be involved with recognizing abnormal cells, infected cells that don't look like your normal cells. The humoral branch of the adaptive immune system, this will involve the B cells. They will activate what we call plasma cells, which will produce antibodies against whatever that specific foreign infection. Now, along with the immune system, it works with the lymphatic system. So just kind of a quick review. The lymphatic system is composed of the lymph vessels, some of the tissues and organs. The purpose is to be recognizing, always searching for any type of foreign substance in the body. The lymphatic vessels, they do move the fluid, which is lymph. It's similar to the blood plasma. What happens is, as the blood is circulating through the body, when the blood gets to the capillaries, which are the thinnest in terms of the thickness of the cell walls of the vessels, and this is where the nutrient and gas and waste exchange occurs throughout the body. Typically, you have a lot of fluid leaking out at the beginning of the capillary bed, and then it's reabsorbed at the other end, at the end of the capillary bed. But oftentimes, not all, 100% of the fluid is reabsorbed back. And so what happens to that fluid? It's between the cells. So it's in what we call the interstitial space. It's between the tissues, between the cells. Well, if enough of this fluid is leaking out, you would start to see swelling. So you have to get that fluid back into the blood circulation to maintain the proper amount of blood volume. You want the amount of blood volume to remain relatively constant. So you have to get this fluid that has leaked out back into the blood. How are you going to do that? You're going to do that by the lymphatic vessels. So these vessels are throughout the body. They're more or less a one-way system. and will draw that lymph, that fluid that has leaked out. It will go throughout the lymphatic vessels. It'll go. It is going to be returning right up in this area, is where it's going to return into the blood flow. Very quickly, what are some of the lymphoid organs? The red bone marrow, the thymus are the primary ones. Secondary lymphoid organs are the lymph nodes, the spleen, tonsils, and what we call the mucosa-associated lymphoid tissue, which we abbreviate as. When we're talking about the adaptive immune system, something that you have to understand is the difference between antibodies and antigens. Antigens are going to be on the foreign substance, whether it's a bacteria, a virus, whether it's pollen, whatever it is, the antigen is on the foreign substance. And that is part of what your body is going to be recognizing, that it is not part of you. And so it's going to want to attack and destroy it. So bacteria, one thing that makes a very good antigen is a protein. So oftentimes the cell walls of bacteria, fungi, protozoans, etc. will have proteins extending out on the surface, and those will often act as very good antigens. It will stimulate your immune response. That's a good thing to help protect you. That's also something that we look at when trying to develop vaccines. Now, other things such as food, notorious things such as peanuts, shrimp, etc., they can also have antigens on them, which can trigger the similar type of response, and you may be used to in referring to as an allergic response. So this is just showing that you do have these antigen, sometimes referred to as the epitopes, that are on the surface of that foreign substance, and then this is what your body's going to recognize. Exogenous antigens, these may include things like toxins, components that are on the cell wall. Endogenous antigens, these are produced by microorganisms that will reproduce inside your cell. And this just shows examples of. Another thing that is mandatory that you understand in how the adaptive immune response is going to work is what we call the MHC. This is the major histocompatibility complex. The MHC, this is a group of proteins that are also on the outer surface of your cells. And this is what by itself, your body, those macrophages, they see that, okay, yours are unique to you. So the body sees your MHC complexes, and it's like, okay, that's fine. That's part of you. That is self. So this is how it distinguishes between self and non-self. Everyone has MHC complexes, but they're all slightly different because they're all unique to each individual. So mine would look different from yours. So my macrophages would recognize yours as being foreign, as non-self, and therefore would attack it and destroy it. Now, one thing that the MHC will do, there's two different classes of them. Class 1 is on all of your cells except for your red blood cells. In class 2, these are present on certain cells that we call antigen-presenting cells, or APCs. This would include things such as the macrophages and your dendritic cells, whose job is to carry out phagocytosis. So what you see over here is a class 1 MHC. This would be this dark blue. This is the major histocompatibility complex. That's going to be on every cell except for your red blood cells. The class 2 is going to be on your macrophages. It will be on your B cells. It will be on the antigen presenting cells. So these are extending out from on the outside of the cell, so all other cells can see it. What's going to happen on these sites on the end, that is where the foreign substance or the antigen can. This is an example just of what some dendritic cells look like. So what happens is there's a process that we call antigen processing. And what happens here is typically what happens, you're going to first be making these, or you have these MHC complexes. You engulf some foreign substance, a cell, a phagocytic cell or an antigen presenting cell. Remember, there's the two types, the macrophages and the dendritic cells. So they have engulfed some foreign substance. Let's say it's a bacterium. And these were those antigens, those markers on the outer surface of that bacteria. So the cell engulfs it, and what it does is it is going to put those antigen markers on the MHC1, on that antigen binding site. So it's going to bind like this. And eventually, there's several steps here, but just eventually know that then on the outer surface of the cell, of the antigen presenting cell, it now has the MHC, the blue complex, but the green is the foreign antigen. And this is why we call it an antigen presenting cell. It engulfed the foreign substance. It didn't take the whole bacteria. It just took these protein markers, these antigens, and it combines the MHC complex, and it's going to basically show it to the rest of your body. It's a way of saying, okay, look, we engulfed this foreign substance. These little green markers, these antigens, are unique to this bacteria. So how do you know how to find that bacteria to attack and find it and destroy it before it can cause disease in you, or before the disease process can get worsened? You need to destroy the bacteria. How are you going to find it? Well, what the antigen presenting cell is essentially showing to all the rest of the macrophages, okay guys, here, this is what you need to be looking for. The T cells, these are initially produced, all lymphocytes are initially produced in the bone marrow. However, the T lymphocytes are going to then move to the thymus, and then that's where they will mature. The T cells will circulate throughout the lymph and the blood. Some of them will migrate to the lymph nodes so that they're present there. Like I said, the lymph nodes are filtering systems. Some will be in the spleen, and also Peyer's patches, which are locations of them associated with the intestines. They do have different receptors on these T cell receptors, or TCRs. They cannot recognize the antigen by itself. The only way they can recognize it is with it is when that antigen or that epitope is with the MHC protein. So that means the antigen presenting cells have to show it to the T cells before anything can happen. So this is just showing the T cell receptor of what that looks like on the surface of the cell. There are several different types of T cells. We're going to look at 3 main different types of them. And then later we look at how all of this comes together. You have cytotoxic T cells. As the name implies, its job is to kill other cells. It's the killers. That's what it does. The helper T cells, there's 2 different types of these. And what their job is to do is to help activate and regulate the cytotoxic T cells, basically tell them, okay, you're on, here's a job to do. They also will help to activate the B cells of the humoral immune response. So this is where you start to see, overall you have the adaptive immune response, then that's subdivided into the cell-mediated, which are the T cells, and then the humoral, which are the B cells. The helper T cells are the link between cell-mediated and humoral. Why? Because the T cells are going to be activated first, and then the helper T cells will activate or turn on the B cells. And then the other type of T cell you have is the regulatory T cells. They're going to kind of help keep everybody in check. So this is a table just showing some of the characteristics of these different types. The regulatory, cytotoxic, and as I said, there are 2 different types of helper T cells. A subgroup of the helper T cells are known as the CD4 cells. The cytotoxic T cells are often referred to as the CD8 cells. We're going to hear that again at the end of this chapter. The T cells, you need to be careful as they're being activated and being made that somehow they don't suddenly turn and see the antigens, see markers on your cells as foreign. If that happens, that's when you have an autoimmune disease. There is a process of regulating and controlling and monitoring so that if a cell starts to recognize markers on your cells as foreign, especially in the very early developmental stages, it will shut them off and destroy those cells. So your immature T cells, initially, those that cannot recognize that MHC complex, they're going to undergo a apoptosis, which is basically self-suicide. That they will die. T cells that will recognize antigens on you, they're going to die. There are some T cells that will become the regulatory ones, and then others that are able to recognize MHC proteins, they're going to become involved in further mature helper and cytotoxic ones. So what happens? Here's your stem cell. All cells initially start as stem cells before they differentiate or specialize. So this would be in the red bone marrow. Then these stem cells move to the thymus. So these are the precursors for T cells. They mature now into T cells. So now it's kind of like step 3 is the process by which, okay, can you recognize the major histocompatibility complex that's shown to you? If the answer is no, I can't recognize that, cell death. If you can recognize it, then it's going to be, okay, great. Do you recognize this as something foreign? Do you then yes, boom, it's going to die. Of the remaining few, some of them will become the immature cytotoxic T cells, and some become the regulatory ones. So there's a whole process of to make sure it doesn't get out of hand. For the B cells, these are found mostly in the spleen, the lymph nodes, and in the malt. There's some that will circulate in the blood. The main purpose of the B cells is antibodies, but they're not doing it continuously. They only do it once they have been activated. And so each B cell has what we call a B cell receptor. And essentially, the B cells, you can read through all this, essentially it can only recognize one, and that's what will happen. Antibodies, this is what you make. Antigen is something that is foreign. Antibody is something that you make. It is going to be made by certain activated B cells that are called plasma cells. What are antibodies? They are what we call immunoglobulins, a type of protein. And there are certain sites where that can bind to a specific antigen. So this is the classic shape of what an immunoglobulin or an antibody will look like. There's different types we'll see later. It kind of looks like a Y. These longer structures on the inside part of the Y, if you will, they're longer. So these are known as the heavy chain. These shorter ones, they weigh less. They're called the light chain. The tips of the Y are the variable region. This is what is different between each one of them. The bottom portion of it is the constant region. That is the same from one antibody to another. As I said, the antibody can bind to the antigen, the foreign substance, and this is on the tips of the Y, if you will. That is where the antigen is going to bind. That is very, very specific. So if it can bind to E. coli, that is the only thing it will bind to. It will not bind to the influenza virus. It will not bind to loblolly tree pollen. What is the function of the antibody? Why do we have it? They're made in response to this foreign invader. The antibodies have several different functions. When they bind with the antigen, they can activate that complement cascade process that we talked about in the previous chapter. Remember, complement was that process of where certain proteins have to be activated in a certain order. Ultimately, when you see complement, as I mentioned last time, what happens, it's going to lead to the death of whatever that foreign pathogen is. So the antibody-antigen complex, when the antibody binds with the antigen, this will activate that complement system. And the complement system itself also activates the inflammatory response, which is good because that's going to bring more macrophages to the area. It's kind of like, okay, I found one of the foreign invaders and I'm just attached to it, but I need to call back up. And so that's going to attract more macrophages to the area who will also be able to recognize, oh, here's the foreign invader. How can it recognize it and distinguish it from your cells? Because of the antigen, because of these foreign substances that look different from yours that are extending on the outside of the cell surface. Sometimes the antibody response can trigger a neutralization. So if it's a toxin, it can neutralize it. Sometimes it can cause agglutination reactions. All of these different reactions ultimately are going to lead to death of whatever that foreign microorganism is. So it may neutralize the toxin. Whenever the red here is the antibody, the little green are the antigen, so you can see how the antibody is binding to the antigen. When you get a large complex like this is like putting red neon lights, flashing lights to say to the macrophages, here it is, come engulf it, eat it up, which is what is happening right here with opsonization. Agglutination, once again, it's binding, clumping it together. Sometimes certain substances may be too large for a macrophage to engulf, and so you may surround it completely and then start secreting chemicals that will then kill the cell. So it's like you're flagging it. There are different types of antibodies. Part of it has to do, the different types have little different functions and locations. The 5 different classes of antibodies, you have IgM. These will be the very first antibodies that are produced. IgG is going to be the most common, and that's the most long-lasting one. When you hear people talk about long-lasting protection, it's going to be involving the IgGs. IgA is associated more with body secretions. IgE is seen more with allergic reactions and parasitic infections. IgD, we do not know the exact function of them. We do know that they are there, but that's an area of, so maybe you can come back years later and let us know what they are. This table excuse me, does show what the structure looks like. As you can see, IgM is a pentamer. There's 5 of these basic complexes together. IgG, IgE, and IgD are monomers. There's just one of those complexes. IgA is a dimer, meaning you have 2 of them that are connected together. Once again, the function is mentioned, the location is mentioned, and overall, the percentage of these that are found. So you can see about 80% of them are your IgGs. When their B cells are being produced, there is what we call a clonal deletion. In other words, you once again start off with a stem cell. This will be in the red bone marrow that the B cells are going to mature. And there is a process by which, if they cannot recognize or work properly, they'll end up dying. In this case, you have one that's recognizing your major histocompatibility antigens, and so that obviously would end up resulting in autoimmune disease, so those cells die. Cytokines are chemicals that are going to be released by cells. They often act as a signal. There's different types of cytokines. Some of them are interleukins. You have interferons. Growth factors can act this way. So there's several different classes of them. And here it shows some of the different types of interleukins and interferons. Interferons we're finding are helpful in showing other cells essentially that there's a cell with the virus. Cell-mediated immune responses, this tends to respond to intracellular pathogens like a viral infection. It also recognizes your cells that are abnormal, so if, say, cancer is occurring, it's going to respond against this. Essentially, what will happen is that we have our cytotoxic T cells that are going to be activated, and then we're going to have a series of steps that will occur after that. So the first thing that happens is you have, let's say, a dendritic cell. That's what DC stands for. You have its MHC1 on it, major histocompatibility complex. And what it does, it has engulfed some foreign substance. Eventually what it's going to do is show that on the surface of the cell, and then it's going to present that to other T cells. You'll have a memory cell made and activate your T cells. So here is an active cytotoxic T cell. Here's the toll receptor. Here is the CD8 part of the MHC complex down here. And here is a cell that has been infected with a virus. So it's going to be able to recognize that. When the cytotoxic T cells, you're going to make clones of those so that you'll have numerous copies of them. Cytotoxic T cells are going to kill the cells. There's a couple different ways that it can. That's the final result. One of the most common ways that it's going to do this is it will produce what are known as granzymes and perforins. Perforins are essentially these structures, and it's like you're putting together this circular design here that ultimately ends up with a pore. You're making a hole here. And then you're going to take these granzymes and dump them in, which eventually will trigger the cell to carry out essentially cell suicide. It's going to kill the cell. This is another process that it can use, CD95 process. Once again, it's going to activate enzymes that will trigger the cell to go through apoptosis or cell suicide. Memory T cells, these will be some of the T cells that will be activated to become memory. The whole purpose is so that they're not dealing with the infection right now, but they will recognize it on any future and subsequent exposure, and they can start the process right away to prevent you from developing. You'll have an infection, but you may not develop the disease. It's a protective mechanism. The memory response is very quick. When the first time you're exposed to something, there's a little bit of a lag time for the adaptive immune system to kick in. You've got to activate these T cells. You have to activate the B cells to make the antibodies, and all that takes a little bit of time. On any subsequent exposure, the response is going to be very quick because you have those memory cells. It's like, oh, we've seen this before, guys. We got to kick in and start working. The regulatory T cells are going to be helping to regulate all this so that this basically so your cytotoxic T cells don't get too out of hand. Antibody responses will be triggered and activated. Very specific type of antigens. And the process that's going to happen here, excuse me, is that you have some of these helper T cells. They have the CD4 marker on them, so we sometimes refer to these as the CD4 cells. You have an antigen presenting cell that has engulfed a foreign substance. It presents the antigen on the surface. So now your CD4 cells or your helper, this is a type of your helper T cells. They're like, okay, we now see this complex here. We need to make several copies of these. We need to make clones of them. And what's going to happen? We need to be able to recognize this particular antigen. Some of the helper T cells will activate the B cells, basically saying, this is what you need to be looking for. You need to make antibodies against this. These activated B cells essentially become plasma cells. A plasma cell is an activated B cell, and its whole purpose is to produce antibodies. And what happens, these antibodies will now go out and bind to the antigen. Some of the cells will become memory B cells so that you always have some of those antibodies present, once again, for future exposure to try to start a response and activate things right away. These plasma cells are very short-lived. They only live typically for a few days. However, the antibodies that they make while they're living can last a long time. And like I say, you will have memory B cells that can start antibody production again if that antigen. So your primary immune response, usually you only need a small amount of antibodies produced, but there is this delay. It may take up to several days to get a response. Secondary future responses will be very quick because you have the memory cells right away. This graph is showing here, excuse me, that you have been exposed. In this case, the example is the tetanus toxin. So there's a delay of about 3 days before you see any response. The initial response are your IgMs. And you can see the level is right about here with this red line. It will last for several days, and then that's going to go down. You do have some IgMs being made. They are made secondary. So after, it takes a while, about 2 weeks to get the development of these. The level, this antibody does stay for some time period. Now, if you were to be exposed to this toxin again, remember the initial primary response, you did not see anything at all until well after day 3. It was right about here before you finally saw a peak. Now the response is much quicker, and notice the IgG response is very, very fast as compared to the primary response. That is why sometimes people will say, oh, you can only get this disease once. Yes and no. Remember, we use a difference in definitions of infection and disease. Infection is when the organism is in you. It may not cause disease. Disease is abnormal physiological functioning. So you've altered your normal physiology. You've altered the way things are normally running. So you can have an infection without a disease. Usually the first time you're exposed to something, you have that primary response, and you may start to show some symptoms. They may or may not be severe. It just depends on your immune system, your exposure rates, etc. But you may be showing fever, you may be coughing, sneezing, depending on what type of infection it is. So you often do show mild signs of the disease, at least. On any subsequent exposure, you have infection because the organism has penetrated, it's in you. But you may not have disease because it may not alter your normal physiological functions. Why? Because the numbers can never get that high to cause the disease. Why? Because your immune system has recognized immediately and has been activated immediately. Oh, we've seen you before and we're going to take care of you. So you never even know that you're infected. with the immune response. Just a quick kind of review right here. Remember the innate or non-specific, that has your first line of defense, the chemical and physical barriers, your skin, things like that. And then the second line of defense, cells being able to carry out phagocytosis, the inflammatory response, the complement system. The adaptive or specific defense, oftentimes called the third line of defense, this is very specific as to what the particular invader is. This is subdivided into the humoral immunity, which deals with your B cells, and cell-mediated, which are your T cells. Specific immunity can be acquired a couple different ways. It can be naturally acquired because you encountered it just in your normal daily living, or it may be artificially acquired. And then we will distinguish it as either or passive. So on this chart, if it is naturally acquired and it's active, it is the way the body responds when you actually had the infection. You were actively and you were naturally exposed to, say, the flu or chickenpox, measles, whatever it is. You were exposed to it. You made the antibodies to it. This will give you very long-term protection against it if you ever see it again. Naturally acquired passive, you have been exposed in some aspects, but you are not actively making the antibodies against it. The classic example is with a newborn or a young infant who is breastfeeding. The mother has antibodies through the breast milk. The newborn or the young infant is able to get antibodies from the mother. Is the baby making antibodies? No. It's getting the mom's antibodies. That's giving it protection. Will this confer long-term protection for the baby? No, it will give the baby protection right now, but not long-term because it's not making its own. It's getting the antibodies from mom. Artificially acquired active. You will be making your antibodies, but you were not naturally exposed. This is what vaccination is doing. When you receive an immunization, you're vaccinated against particular disease, you are exposed to part of an antigen on there that triggers the immune response, so you build antibodies against it. This will give you protection long term. Did you actually have the disease? No, you did not. That's why it's called artificial. And then artificially acquired passive immunity is when, once again, you were not exposed to the antigen, but you are given antibodies, pre-made antibodies. So active, you make your antibodies, that's going to give you long-term protection. Passive, you're not making the antibodies, you're being given the antibodies, either as an infant from mom or you're given pre-made antibodies. The artificially acquired passive is often used with someone who maybe is immunocompromised, who cannot receive a vaccine. Maybe they're allergic to some of the components in it. Maybe their immune system is already suppressed for whatever reason. They cannot get the vaccine. They cannot be exposed, but they need protection. So you give them preformed antibodies. It will protect them for right now. Once again, does passive confer long-term protection? No, it does not. You can find this on YouTube. It'll be free. I will be showing another slide in the files, just with additional